there are a few things to note about this week, okay? So first off, when it comes to starting today, you'll need your notes first. So like just your regular notebook paper. We will get to the packet later today when we work on practice. Here's what's going to happen. Today we're going to learn to do heat of phase change calculations, aka 5Q problems. You'll see why they're nicknamed 5Q problems, but that's what we're doing today. And then we're going to practice at the end of the period. Tomorrow, we're going to practice, and then you'll have your lecture quiz tomorrow like normal, only tomorrow's lecture quiz is a little beefed up, okay? It's worth 12 points instead of 6 points. Here's why. Today's lecture question quiz is just basic concept questions, no calculations today for the lecture quiz. Tomorrow, you're going to have a mini quiz over the calculations I teach you today. So today I'm going to teach you calculations, you're going to practice them. Tomorrow you're going to practice them even more, and then you're going to take the quiz in the second half of the period, okay? So that means that tonight you really want to make sure you're going to get in some good practice, okay? Now, so we're going to quiz on Monday and Tuesday like always. Wednesday it's going to be our review day, but it's going to be for the whole unit because the Unit 3 test is this Friday. Thursday, virtual people, you don't need to come see me. You live people, we got the Burning Food Lab, which is a really fun one, setting Cheetos on fire and stuff. It's a good time. And then Friday is the Unit 3 test. Okay, so that's what we got coming up here soon. Now, what I really want to emphasize about today's notes, it's going to be a lot of math. When I say a lot of math, I mean it's only multiplication and addition. It's not like very difficult math. Math you guys have done before, you've done much more difficult math. But there will be problems where you might have to write like 24 numbers. Okay? So there's just going to be a lot of numbers for these. And I'm not trying to stress you out, but what I am trying to emphasize is that you need to be nice and organized today. And I'm going to give you a system. I'm going to give you a system that would be very organized, very structured. I'll help you. Okay? But I just want you to know that you need to leave nice, good space, write neatly, have a good structure as you take your notes today. Alrighty. So 5Q problems, aka the energy associated with phase change notes. Now, 4.18, it's fine for liquid water. That's the guy that we are used to. Okay? But that actually only works for liquid water. What about if we had ice or steam? So I'm about to reveal a couple numbers to you. You do not need to memorize these numbers, but I do suggest that you write them down because you will use them today. So the specific heat capacity for solid water is actually 2.06. So liquid waters are 4.18, as always, but solid water is now 2.06. And this number right here, you will be given this number whenever you need this number. Any quiz, any test, I will give you this. But I do suggest you write it down. Liquid water is a 4.18. Many of you probably don't want to write down this middle column, which is fine by me because you already know this number. And when you have gaseous water, its heat capacity is 2.02. When I say specific heat capacity, of course, I'm talking about the C, remember, the C from Q equals MC delta T. So these are all the C values. So the specific heat capacity of a substance will change depending on what phase you're in. It will change depending on what phase you're in. Okay. Now, if we remember these graphs from last week, we talked a whole lot about these graphs of like, hey, I can ask you about kinetic energy or particles or, you guys know what the quiz was like last week. I asked you a lot about what's happening in the different parts of this graph. Now, today, we're actually going to calculate the numbers in terms of energy to go through this graph. So we've never really done any calculations involving this graph. Today, we're going to take the calculations and impose them on this graph. And again, just an FYI, when we're talking about like 4.18, you don't have to draw this. Remember, that only applies to liquid water only. So this whole section, where it's just liquid water, that's where the 4.18 applies. It does not apply to like this flat line where we have a phase change, okay? That doesn't apply there. Now, here's an idea. So we know Q equals MC delta T. Again, you don't need to write this down. You've written this a million times. You know this equation. So here's our heat equation we're used to. And it's fine for each phase of matter when you have only solid, when you have only liquid, only gas. But here's the thing. It's not very good for phase changes. Q equals MC delta T is not an equation that works for phase changes. And again, I'm talking specifically about this section of the graph where we have a phase change and this section of the graph where we have a phase change. Why does Q equals MC delta T not work for phase changes? Anyone have any ideas on why that might be?
It's in between two different states.
That's true. So like, wait, which specific heat capacity do I use? Mr. Williams, did you have an idea back there?
Because during phase change, the temperature does not change.
That is exactly why this won't work. So Q equals MC delta T requires an M, a C, and a delta T. During phase changes, there is no delta T. This whole phase happens at 0 degrees Celsius. This whole phase change happens at 100 degrees Celsius. So we don't have a delta T for this, so that's why there's a problem. That's why there's a problem. So it doesn't work because there is no phase change, or there is no delta T during phase changes. And so Q equals MC delta T will still work for the sections of this graph where we do have temperature change, but not for these two I have circled here. And so that brings us to a new equation, which is actually a little bit simpler than Q equals MC delta T. It's Q equals M delta H. So I have state change written here because it'll depend on whether you're melting or freezing or vaporizing. The shorthand version of this equation is simply this. Q equals M delta H. Okay? M stands for the mass. And the delta H is some given value. It's a constant. I will always give you the delta H, so you do not need to memorize or calculate the delta H. I'll just give you that. Okay? And again, this equation applies to these two sections of the graph where we have a phase change. There is no delta T, so we can't use Q equals MC delta T. But when we have that situation, we'll be using Q equals M delta H for there and there. Okay. So, the heat of fusion applies to melting and freezing only. Melting and freezing only. By definition, the heat of fusion is the energy that you need to melt or freeze exactly 1 gram of a solid at its melting point. For these problems, we're only going to talk about water, so that melting point will be 0 degrees Celsius. Okay, so it's the energy needed to melt 1 gram of solid ice, or it's the energy needed to be removed from liquid water to make it freeze. So again, the Q of fusion will be equal to the M times the delta H of fusion. And this number I'm about to reveal here, do not need to memorize it, but I would write it down because you'll need to use it today. But the delta H of fusion is 334. So absolutely write this down because you'll be asked to use it here shortly. But you don't have to memorize this. I will always give this to you. Any quiz or test will have delta H fusion equals 334 written at the top. So you'll always have that, but you will need to use it today. Okay. So, for example, let's say I'm starting right here on this graph where I have a bunch of ice that's at 0 degrees Celsius and I want to melt all that ice. And I want to go to this point of the graph right here where it's all melted. So let's say I had 100 grams of ice that I wanted to melt. Oh, hello. How much energy would that require? Well, here's how much that would require. So during a phase change, Q equals M delta H. And in this particular case, our M is 100. And our delta H, since we're melting or freezing, would be 334. And so that comes out to be 33,000 joules. Now, to clarify verbally what I mean by this, what I'm saying is, if you want to melt 100 grams of ice, you need to pump 33,400 joules into it. Or, if you want to freeze 100 grams of liquid water, you need to take 33,400 joules out of it. Does that kind of make sense? So we're never going to worry about negative or positives on these. They'll always be positive since they're Q's. And the way we'll indicate which direction it's going is by saying, oh, this energy is absorbed or this energy is removed. Does that make sense? Okay? So if we're going this way, we're melting it. That energy is being absorbed, is going in. If we're going this way, that energy is being removed, is being released, that kind of thing. Yes, ma'am.
I have a quick question.
Okay. What's up?
So I've heard that hot water freezes faster than like room temperature water. Is that true?
Hot water freezes faster than room temperature water. I've heard that one before too. By the end of today, when we are calculating the joules on things, you might be able to answer that yourself. So hold that thought. I love that question, and you might be able to answer that yourself later today. Okay? Alrighty. Now, this only applies, okay, this number right here only applies to this part of the graph right here, where it's melting or freezing. Only, okay? So I sometimes kind of call this the cheap, you don't have to write this, cheap bridge. Okay, so it looks like sort of a bridge on this graph. That's like the cheap bridge, okay? Or sometimes people call it the fusion bridge. However you want to think of it. But this is the price to pay when you want to go across that bridge either way. Now, if we want to go across the higher bridge, okay, that's involving heat of vaporization. Heat of vaporization. So this is when we're talking about vaporizing or condensing your water. This is the energy needed to vaporize or condense 1 gram of a liquid at its boiling point. So again, for water, that's going to be at 100 degrees Celsius exactly. It's going to be 100 degrees Celsius exactly. So your equation will be Q of vaporization, so the energy to vaporize, is equal to the mass times the delta H of vaporization. This number that's about to appear here is not a number you need to memorize, but it's a number you should write down. The delta H of vaporization is actually 2,260, which is a lot higher price. And this number, it only applies to this section right here. It only applies to this section right here, that phase change. And so I sometimes call this the expensive, quote-unquote, expensive bridge. You do not have to write that down or use that term if you don't want. So below, when you're melting or freezing, that's kind of a cheap bridge. Here, when you're either vaporizing, or sometimes people will say boil, or condensing, it's the expensive bridge. Okay? So you have to pump in 2,260 joules into every single gram of water that you're trying to take across that bridge. Okay? Or if you're going back that way, you have to take out that many joules. Okay. So now we're about to do our first practice problem. And here's where I really want to emphasize, okay, here's where there's going to be a lot of math, but as long as you're nice and organized, you will be in good shape, okay? I will show you exactly how I do these problems, exactly how I break them down. Now, here's what I like to do, okay? I like to redraw the graph. You do not have to do this, but I suggest that you do it because I think it will really help you prep for the problem. So here's how I redraw that graph. I keep it simple. I focus on the shape more than anything. It goes up, it's flat. It goes up, it's flat. It goes up. Looks familiar, yes? Hey, melting and freezing of water takes place at what temperature? 0. And boiling or condensing takes place at what temperature? Okay. So if you can reproduce this shape in those two numbers, I think you'll be in pretty good business. Pretty good shape, I should say. Let me show you why I like to redraw this graph on each one of these problems. Okay, so here's the situation. How much energy is required to warm 265 grams of ice at negative 15.4? So this is our starting point. We have that much ice at that temperature. And we want to warm it all the way up to steam at 185 degrees Celsius. So what I'm going to do on the graph is I'm going to find my starting point. I'm going to find my ending point. I'm going to trace how many Q's I need to calculate. So I'm starting at negative 15.4 degrees Celsius. Where would that be on this graph? Which section? Between 0 and 100? It's negative 15. Right, so it'd be somewhere in this section. We don't know where. We don't care either. We just want to know what section. it'd be, oh my, did I go backwards? There we are. It'd be somewhere around here, so I'll put a big red dot right there, okay? Where would 185 degrees Celsius be? Yeah, above 100 somewhere, so let's just say right there. It doesn't really matter. So I'm starting here, I'm going to here, so I'm just going to trace, I'm going to count how many sections I need to go through. Okay, so I have to go from here to here, that's one section. Here to here is two sections. Up this slope is 3. Over here is 4. And finally to get to that point, that's 5. So that means I have to calculate Q 5 times. This is the maximum number of times you're going to have to calculate Q. So what I do the moment I count how many Q's I have, I write them all in a row. Q1, Q2, Q3, Q4, Q5 to be nice and organized. You don't have to write these numbers 1, 2, 3, 4, 5 over here. Don't worry about that. I would just write on your paper Q1, 2, 3, 4, and 5 in order in the nice little column so you keep everything structured and nice and clean. Okay. So, the first thing we need to do is we need to go through this section of the graph right here. So we're going from negative 15.4 up to 0. Yes, sir? This is just notes, and then right after this problem, then we'll be back in the packet.
Okay.
Yep, good question. So we need to go from negative 15.4 degrees solid ice to 0 degrees solid ice, because that's where we hit a turn in the graph, okay? So, what we're doing is we are warming the solid to 0 degrees Celsius. And you guys don't have to write this part down if you don't want to. I would just focus on the Q's if that's what you want to focus on. Or you're only going to pick one. Okay. Now, Miss Bree, is there going to be a temperature change in this section? As we go from here to here. There is. What kind of temperature change are we talking about? Well, actually, you know what? Before we get there, if we know there's a temperature change, that means we know we're going to be using Q equals MC delta T, and not the Q equals M delta H. So we know we're over here, okay? Bree, what is our mass for this problem? $265, so that's the first number we plug in for our M. Get used to that. They all start with M. Okay, now, Bree, this is currently ice. This is solid H2O. So Q equals MC. What is my C for solid H2O? Yep, it's 2.06. You're like, wait, Mr. P, where did she get that from? She got that from right here. Remember, this is the heat capacity of solid H2O. And then, Bree, just for this section only, going from here to here, what's our delta T? What temperature are we starting at? Negative 15.4, and then what temperature are we at right here? Yep, so what's our delta T? Yep. Some people are going to want to try and say, like, oh, you have to go from 15.4 to 185. That's true by the time we're done, but for just this section, we're only going up 15.4 degrees. Because the moment we get to 0, then it's going to start melting, and we have to calculate things differently. So if I plug it into my calculator, I'll get 8,400 something. I write that down, and I leave it be for now. I'll worry about this at the end. So I write this out. Do you see how this is all in one nice, clean line? Structure, organization, clean. That's what we're looking for. Okay, our next section, we're going from here across the cheap bridge to here. Let's see here. Barrick, is our temperature changing at all as we go from here to here? No. So are we going to use Q equals MC delta T? No, we're not. We're going to use Q equals M delta H. All right, so as we melt all that ice, what's our M here, Barrick? What's the M for this situation? Love it. Okay, and what is our delta H for the cheap bridge, the fusion bridge? It might be kind of hard for you to read that, so that's why I had you write it down earlier. The fusion bridge, which one? The cheap one, what is that? A little hard to see it. That's the expensive one. This is the one where it's just 334. Because this guy right here, that applies to melting or freezing. And again, you'll have this on all your worksheets from now on. But I had you write down it earlier because it's kind of hard to see up here because it's pretty small. And that's it. That's your M, that's your delta H. You plug it in, you get 88,000. In other words, it's pretty expensive to melt something. Okay, so we've done 2 sections. Now we're here, and we're going up to here. All right, Melania, is there a change in temperature in this 3rd section? Yes, so we're going to use Q equals MC delta T as we warm the now liquid to 100 degrees. What's our M, Melania?
265.
Love it. What is our C for liquid H2O?
4.1.
Absolutely. What is our change in temperature for this section only?
100.
It's 100. So if you're like, wait, but you started at negative 15.4. You are correct for the first section. We already paid the price to go from 15.4 to 0, so we don't want to pay that price again. We're going to start at 0 because that's where we're currently at. You plug all that in, 110,000 joules to warm the liquid water up from 0 to 100 degrees. Alrighty, so now we're going from here to here. Ms. Mooney, is there a temperature change in this section? No, there is not. So can we use Q equals MC delta T? Nope, because we don't have a temperature change. So we're going to have to use Q equals M delta H. So we're going to boil this now. So M delta H, what's our M, Mooney? Love it. And this is the expensive bridge up here. So what's the price to go across the expensive bridge? Perfect. Yep. So we have 265 grams, and it costs 2,260 joules to take each one of those grams across the bridge. That is going to be a crazy price, almost 600,000 joules. It's usually the most expensive part on any one of these graphs, usually. And lastly, all right, Zach, as we go from here to here, is there a temperature change?
Yes.
Yes, there is. So we're going to use Q equals MC delta T as we warm this gas. What's our M?
260.
What is our C of gaseous H2O?
2.02.
Love it. And what is the change in temperature for this section only? We end at 185. What's the delta T? And you're thinking, where did you... This section is from here to here, here to here. What temperature did we start at down here?
100.
What temperature did we end at? So what's the delta T of this section?
85.
Correctamundo. And you'll notice we did ultimately go from negative 15 to 185. So here's 15.4, here's the 100, here's the 85. But we have to keep them in their specific sections where they use the heat capacities of the liquid, of the solid, of the gas when appropriate. So you plug all that in, 45,000. So at the beginning of the problem, I knew I had to calculate 5 Qs. I have calculated all 5 Qs. What am I going to do with these 5 Qs now to find the total cost? Add them all up, that's right. I add all these up. I get 852,000. I'm a model student, so of course I'm putting a beautiful box around this with my units. And now I'm done. What this is saying is, hey, if you want to melt 265 grams of ice that's currently stuck at 15.4 degrees Celsius, at negative 15.4 degrees Celsius, if you want to melt that and get it all the way to the point where it boils and it becomes steam that's 185 degrees Celsius, you will have to pump 850,000 plus joules into that ice to get that to happen. Okay? Do you guys see how the math itself is not super difficult, but the organization is key? I mean, look how much stuff you had to write down for this one problem. Okay. Now we can transition over to the energy calculations involving phase change practice number 1. It's in your packet. Make sure you start with practice number 1 and not bell work number 1. The titles look very similar. So it's energy calculations involving phase change practice number 1. You'll notice at the top you have that beautiful little chart with all the numbers. You will always be given this little chart with all the numbers. It doesn't tell you which equation you're using, like the Q equals MC delta T, that kind of thing. You need to know that. But these numbers will always be provided. Okay? I'm going to start this next problem for you to keep the gears turning, and I'm going to let you guys work independently. So, calculate the number of joules needed to turn 525 grams of water at 100 degrees to steam at 100 degrees. Please notice I have created my poor man's version of the graph over here, where I basically just drew the shape. I'll plop in my 0 and my 100. Mr. P is never going to grade your graph here, but he will see, hey, if you're drawing graphs like this, I see that you understand what you're doing. Okay? I think it'll help you be structured. Okay, so where am I starting here? Mr. Williams, can you tell me where on this graph I'm starting? It says I have 525 grams of water at 100 degrees Celsius. So where would I be starting here?
At 100 degrees.
100 degrees, okay. So somewhere on this line here. But where exactly on this line? Should I start on the left, on the right, in the middle? And how did you know that? It does go up, but why did you start here and not here? This is 100 degrees too. Why did you know to start on the left-hand side of that flat line?
Because you read left from right.
But what if we were removing energy? It would be going the opposite way. What phase is this starting?
Liquid.
Liquid water, right? So it's liquid right here, it's all gas right here. So that's how we know to start on the left, because that's where it's all liquid. So then, Mr. Williams, where does this particular graph end?
It should be at steam.
Mm-hmm.
So it'd be at the top of that, of the line.
Right here?
Yes.
So right here, is this above 100 degrees or at 100 degrees?
Above. Are you saying just where the 100 degrees is?
Yeah, this is just where this is asking us to go.
Okay, so at the end of the horizontal line.
Yeah. So just right here, because this ends at steam at 100 degrees, it's not asking us to warm that steam up. All it's asking us to do is basically boil this liquid water. Does that kind of make sense? So how many sections are we using? Just one. So this particular problem, you only have to calculate one Q. I call these 5Q problems because at maximum, you'll have 5 Qs to calculate. That does not mean you will always calculate 5 Qs. So I just write my 1 Q. Let me see here. Mary, is there a temperature change here? Nope, so I'm not going to use Q equals MC delta T. I'm going to use Q equals M delta H. My M is 525. And what delta H should I be using here? And is this the cheap bridge or the expensive bridge? So what delta H am I using? Yep. So I calculate that. That comes out to be just over 1 million. And I have nothing to add that to because I only have to calculate 1 Q. And so that is actually my final answer. Okay. Couple of things before I let the virtual folks go. Number one, you do have a Monday quiz today. Your Monday quiz lecture questions do not have any calculations of any kind. There's no calculations, it's just concepts. Basically, do you understand the ideas of what we're talking about? Tomorrow will be calculations just like this. Secondly, the answer key to the worksheet you just started is in the Monday folder. So you can do a couple, check a couple, that kind of thing. You've got to finish this whole worksheet before you come in tomorrow. You just have to, because you need to make sure you will practice, you're ready to go. Because tomorrow we're going to come in, we're going to practice immediately, and then we're going to take that quiz in class. Okay? So you make sure you're ready to go. You'll notice in your packet you have this practice worksheet, which is front and back. Again, the keys in the Monday folder. Then you have another whole page. You need to do at least the first whole worksheet. This one, if you want to do some of this tonight, you can. If not, I'll give you lots of time to work on this one tomorrow. The answer key to this is in the Tuesday folder and Monday folder, I believe, is in both. Then we even have a little bell work. So you guys have lots and lots of problems for which you can practice. Okay? So I'm telling you, you've got to finish practice worksheet number 1 tonight to be ready tomorrow. You just have to. That's the only way you're going to be prepped. So most of you may want to take that lecture question quiz right now. You don't have to if you don't want to, if you'd rather practice. But that's what we're doing. Okay? So, virtual folks, if you have any questions, please stay on the line and let me know. If not, you guys can get out of here.